And now we turn to the third question that we can ask about span. And so that is, well, before we get to it, I'm going to give a new definition. And so that is, for a vector space V, if you have a set S such that the span of S is equal to V, then S is called a spanning set for V. So our original question from before was, given a vector space V, can you find S such that the span of S is equal to V? So now with our new jargon, given a vector space S, can you find a spanning set for V? So same question, different language. Okay, so let's look at some examples. So from before we saw that for Rn, the columns of the n-dimensional identity matrix In form a spanning set for Rn. And so again, the idea is just that if I take any vector in B in Rn, I can write B as a linear combination of these vectors in this way. Okay, so let's look at something with a little more meat on it. We've seen from our previous examples that 4, 0, 2, 1 minus 1, 1, 1 minus 1, 2 is a spanning set for R3. And we also saw that if we take the one that's got third element of -1, -3, 1, then that one is not a spanning set for R3. However, if we combine them, so we throw in this guy, then this one is a spanning set for R3. Now, the reason why is because to determine whether or not this is a spanning set, you need to know, can I build any vector in R3? And it turns out that, yeah, in fact, I can build any vector in R3 with just these guys right here. So I don't need that last one, but I can have it. It doesn't hurt. It's just some extra piece of junk that's just, trailing along for the ride. So if I have, throw in a few more things, add on, let's see, this one, and this one, and this one, okay, then this is also going to be a spanning set for R3. It's just got a whole bunch of extra junk in it. In the next section, when we talk about linear independence, we'll talk about how to get rid of extra junk. But for right now, it doesn't matter. It's just got to be sufficient for building everything in R3. And so the basic point that I'm trying to make here is that if S spans a vector space, then so does S union anything else, whatever vector you want to call it. Let's call it Z. So this notation right here means that I'm adding Z to the collection or set S. This particular symbol right here, if you haven't seen this before, this is union. The union of two sets is just the combination of two sets. So in other words, the union of A and B consists of all things that are in A or in B or both.